I think we should. Okay, so we think you have all that you need to do to complete Homework 0 and MP1, except for the following. We know that there are some constructs in MP1 that you're going to have to struggle through and figure out. We know we haven't quite yet taught you the material that you need for little teeny tiny pieces of it. But what we also know is that there are tons of resources available to you to help you through that, to push through that barrier. So, is that more tolerable? Like, I can't stand my own voice. I don't know how you guys do it. Okay, so we know that MP1 has, these little things. But you know what? That moment where you see a piece of code and you go, what the heck? That's authentic. That's part of our stock in trade. And one of the things we really hope that we make you better at through the course of this semester is your own ability to push through those things and check your resources and go, no big deal, I'll just, and have some answer to that. So at this point, for the couple little barriers that you're likely to see in MP1, your resources are the Piazza, open office hours, the queue is live and ready to go, Google by way of Stack Overflow, but probably not GitHub, because you won't learn anything that way. Let's see, I had a fourth. Oh, your lab. When you go to lab this week, you will probably there will probably be time for you to ask course staff in your lab or somebody sitting next to you if they ran into the same problem. So we want to get you accustomed to all the different resources available to you. All right, I also have another announcement. It's very strange to me to be writing this announcement because we haven't ever done this before, but quiz, I think it's exam 1. No, it's exam 1 of 7. Happens next week, so starting Sunday. So it's available for sign up in the computer-based testing facility now. Is it on the website yet, Wade? Did you do? Okay, it'll be on the website momentarily as soon as we actually get it done. It's a CBTF-based exam, computer-based testing facility. It begins 1/29 and goes through 2/1, I believe. And it's a 50-minute programming exam. Oh, look at that. Yeah? Keep going. You can do it. Oh. Okay. The topics that will be covered. Keep going. Go. Okay, fine. 1. Oh, boy. I don't know how this is going to go. We might need to do a refresh here. The topics that will be covered are everything in MP1, everything in Lab Intro, and this week's lab, which I've forgotten what the title is. I think it might be Debug, but it might be GDB lab this week. And lectures through Friday. I don't know how to deal with this. So what I'm going to do is exit out of this. Kill it. Kill it. Damn. Okay, so those will be the contents of your exam. Now, these will be programming exams, so our intent is to give you a little programming puzzle that you solve. You write in your solutions, you upload it to the system. They are not intended to be stress-inducing. That's why we have 7 of them. So we just want you to kind of show us what you know. Let's see. Yeah, especially this first one. Especially this first one, it's going to be much more about process than it is about content and trickery. There shall be no trickery. Is there a question? Any questions about it? In addition, every week in labs you'll have quizzes. So those are that's how we're going to assess what you know. All right, so let's work today. I have here some pieces of code that came from last time. So this is largely a reproduction of the Sphere class that we were working on at last Friday. And I want to know from you specifically what happens when I do that. So assume that my code compiles. Assume that, I've got the compilation process set up so that all the right things, all the right machine is compiled together. And now my question is, when I execute the code, what happens here? And more specifically, do you like what happens here? Do you like it? What happens, and do you like it? Raise your hand if you like it. Raise your hand if you do not like it. Okay? You're in the hot seat. Why don't you like it? Yeah, it gives you a random value. Right, exactly. But wait a second. Last time, we talked about this line of code. We talked about what happened here. A constructor is invoked, right? A constructor is invoked. Well, which constructor is invoked? Right now, in this code that you see here, which constructor is invoked? Is one? Yes. The default constructor that has no arguments, that is provided by the system, is invoked for you. Now, that constructor does not care about your silly little radius. It does not care about any of the memory associated with your object, and so it's quite happy to let everything there be garbage. Okay? Now, when I say garbage, I mean garbage in the sense that it has no value. Some garbage does have value, I guess. But this garbage has no value, which means for us, we can't test it. We can't look at the data and go, hey, are you garbage? Because we have no way of specifying what that value is. Another way of referring to this is that it's an uninitialized value, which means there's nothing to ask. Now, or nothing to ask about. Now, some compilers will be super nice to you, and they will take all uninitialized values and give them an initial value of some kind of 0. But that doesn't, you can't count on that happening for sure. So at this moment, in this state, with this code that you see, you absolutely do not get the anything that you expect out of get diameter. There's nothing to expect out of get diameter. Now, how do you know that? How do you know that that's going to be true? Does anything in the system yell at you and go, hey, you knucklehead, you forgot to initialize your memory? Does that happen to you? No, it's all on you to know it. Okay, there's nothing that says, yo, I'm an uninitialized value. Give me some attention. Nothing, okay, necessarily. Yeah? Yeah, the object creation process is a little bit different in C++. That's right. Here, we just declare it. It's there. It's more like a primitive type, and in fact, we design our objects so that they behave like primitive types do. Okay? All right, so how do we remedy this situation? I could ask, but you would all answer, and that is that we declare and further we define a constructor to do this. Okay, so this is a declaration of our intent to write a constructor, to create a sphere. Let's see, can I do this? Sphere B 5.6. Can I do that? No? Not yet, but I could if only I had yet another constructor. So you can have constructors parameterized in any way that you prefer. So double, we'll call it new rad, doesn't really matter. Okay? Any question about that? All right, and so now there's nothing broken about this. There's nothing broken, but it is incomplete. Notice the comment here, constructors implemented on the next page. That's kind of where we were at the end of last time. So here we go. I wrote them in for you. And again, I'm writing code so as to implement the reasonable behavior upon declaration. Okay, now my question is, if I take exactly this code, add it to the code on the previous page, and do a nice compilation, will it work? Will I have a compilation problem? The answer is yes, I will have a compilation problem. What is it? And the answer is I have two identically specified constructors. So these are alternatives, and we would pick one of them if we were actually making this code work. Okay? All right, so I sort of feel like we're caught up to the end of last time, and I want to go through these points to remember about constructors just so they're all in one place. The first one is that if you don't write a constructor, the system will provide one for you, but you probably won't like it very much. Okay, that was the example on the previous page before we made our own. So if you write no constructor, the system provides one. Okay? A no argument. But it doesn't do anything special with your variables. Okay? Another thing to remember about constructors is you are never going to call them. If you come up to me and you say, can I just call the constructor? I'm going to go into that kind of pedantic mode and go, oh, you don't mean call, because you don't actually call the instructor or constructor. You provide the constructor for the system to use whenever it wants to. So this is sort of, just a rule sitting there for C++ to use when you ask it to make you one of your things. So constructors are not called by client code or any other code. You provide them to the system to use to create objects when you ask it to create objects. Okay? And that's kind of vocabulary, but it's also kind of a best practices issue. Okay, and then the last thing is, well, let me ask you about it. I'm going to do something. I'm going to get rid of these guys and pretend like this wasn't there. Okay, so what did I do? I got rid of the no argument constructors. Okay, now my question is this okay? What do you think? I don't think I've told you this yet, so just speculate on your own. Do you think it's okay to have a constructor that makes this and rely on the default version here? What do you think? No, answer's no. If you write any constructor, then the system will provide none. Okay, so let me write that down, and then I'll have one more sentence. if you provide any constructor, the system provides none. Okay? And luckily, the compiler will yell at you. It'll say, no constructor for that declaration. Send you to that line number. So you'll have to go back and look and see if you get that error message. Okay? But luckily, it's compiler, so we don't even, those are easy. Okay, any questions about all of this? Okay, so I want to take just a couple minutes and kind of step back and tell you what I think you know, and kind of give you some vocabulary words to wrap around some of the things, some of the code that we've seen already, all of this, even very simple code. All right, so basically we have just done a single, simple class definition. But I think you probably noticed that the code for that example came in kind of three parts. There was the interface that is commonly referred to as the class definition that came in our slides in these purple boxes. The class keyword will always appear there. And it's essentially a list of the functionality of the class. And data members. And by convention, we typically refer to it, or we typically break it apart and put the class definition into a file called class.h. File by convention, which simply means we don't have to, we just usually do. Okay? And that was kind of where we started. We also had client code. So for us, you know, we've only used main.cpp as our client code. And we talked about the fact, so these are our clients. We talked about the fact that this is the user of a class. And it shouldn't surprise you that, you know, my example, my main.cpp was only one little teeny tiny, not even very interesting example of a piece of client code that would use the sphere class. You know, you could have any of many different users of a sphere. Spheres are so useful. And each one of those would be considered a client. Anything that ever declared an object of type sphere. Okay? Any question about that? You can't even prescribe the utility of it necessarily. Yeah? Uh-huh. By convention? Uh-huh. All of it is. Actually, there are two things that are done by convention. The first thing is that we separate them into their own files, and the second thing is that we name them the same as the class name. Okay, neither one of those necessarily has to be true. It's just a super good idea to do so, because that's what everybody else in this room is going to expect you to do. Okay? All right. And then the third piece of this is the implementation of the class. This is the guts, right? This is the details of the functionality. These pieces, this implementation, will typically have the scope resolution operator to connect the implementation to the class. So this connects implementation to the class. Okay, like right here, connects that constructor to the sphere class. And this is where you think of the real code, right? This is the part where, you know, we actually do the data munging, data crunching. By convention, we put this in a class.cpp file. Okay, again, two conventions here. One is we put it in its own file. The other is we give it a name that's consistent with the class name. Okay, any questions about that? And that kind of explains the breakdown into the blue and green and purple boxes that you're going to see going forward even. I'll try to maintain that consistency as we go. But there's one more little piece of this. If I had a big enough hand to cover up that green bubble, we could still use the sphere class. We don't have to know at all how it's implemented. In fact, this class interface, this class definition, is a perfect way of communicating to the client exactly what they can do with our class. Okay, and so we allow the client code to see the class definition, the interface, and we put up an impenetrable wall between the client code and the implementation. Partly because they don't need to see it in order to use the class, but partly because this is our stock and trade, right? This is our intellectual property. This is where we have been clever. I found a new and brilliant way of computing diameters. I want to hide it from the clients because I want them to use mine, right? And so we have this nice mechanism in C++ by which we can separate the client code from the gory details of the implementation. The other thing that's important about it is we don't want client code messing with our implementation because they might come in and say, hey, I got a better way of computing diameter, and they might mess it all up. So this wall right here is designed to maintain control over the functionality of your software. Okay, this paradigm for separating interface from implementation is called encapsulation. And I think I have it. Separation of interface from implementation is on the next slide, so you don't have to write that down here. But I do want to make note of the fact that in C++, the class definition can be separate from the implementation. So the class definition and the code, by that I mean the implementation, can be separated even into separate files, which is how we typically do it in this course. And the other thing that C++ does to maintain or to implement the encapsulation paradigm is that it gives you a mechanism for making sure that clients don't mess with your data. And it does it through the private keyword. Protects the data. Okay, any question about that? So I feel like it's a little bit of a compromise because here in the class definition, I'm going to show you this interface, and I am exposing a little bit of the implementation, right? I'm telling the client, I'm making visible what data is important to keep. So that feels a little bit like a compromise of encapsulation, but we do have a mechanism for protecting it even though we expose it. Okay, any questions about all of that? Okay, so this idea of encapsulation, that is separating interface from implementation, makes for much easier to maintain code. So it's a good idea in terms of software engineering and code design, but it's also a characterizing part of a more general notion of object-oriented programming. So it's one element that is oftentimes used to characterize this idea of object-oriented programming. So someday you're going to be in an interview and somebody, maybe even in a little bit of a snooty voice, says, okay, I'm going to get you now. What are the three key words that characterize object-oriented programming? And you're going to be able to whip off inheritance, encapsulation, and polymorphism. Bring it, okay? Now, right now, we have just discussed encapsulation, but later on, we're going to see inheritance and polymorphism as well. Okay, so right now, encapsulation is in your back pocket. All right, any question about that? This is see previous slide. Question about it? Okay, we're going to completely shift gears at this moment. We're going to shift gears away from sort of just, very basic class definition into, well, downward toward memory. And in particular, we're going to talk about how we use language, how we use C++ to control memory, and the mechanics of doing so. Now, it's really hard to draw the line at where to stop and how specific to be with this. I'll tell you from the outset that if you love it, if you want to know more, there are entire courses that give you the background that you need to become completely fluent in manipulating and maintaining memory. That's not this class. We're getting through C++ so that we can get to the data structures portion. But nonetheless, it's important that you have at least a basic mental model of what's going on in memory. So first of all, what memory am I talking about? I'm actually talking about the memory that you decide to buy when you outfit your own machine. It's the memory that the CPU uses to change data, to manipulate data, mostly, sort of. One of the pieces of memory that it does. So that's the memory we're talking about here. This machine still sits in our house, and I had to make that decision. And we made a bad decision at that point. So this is like a 10-year-old machine almost now, which I guess is pretty good, but it does not have enough memory in it because it grinds to a halt after, 10 minutes of Minecraft. It's done. I don't know. I'm kidding. All right. So that's what we're talking about. Now, I don't want to talk about actual memory. I want to do things via a metaphor. What is that thing right there? Can you tell what it is? Somebody in the back row, what does that look like to you? What does it look like? What do you think it is? It's a little slice of Google Maps. If you smear your eyes a little bit, it looks like a memory stick. It looks like, the card that you chunk in, right? But the analogy actually doesn't just do that. The analogy is actually pretty good because just like Google Maps, memory, RAM, in your machine has a mechanism for communicating the location of things. So if I say to you, if you called me up and said, okay, where's the nearest In-N-Out Burger? This was actually taken from Southern California, so it's a reasonable question in the context of this particular map. If you said, what's the address of the nearest In-N-Out Burger, I would say, 3452 Foothill Boulevard, and you would know, you'd know exactly how to get there, right? The same thing is true in memory. There are mechanisms for specifying exactly physical location. Well, sort of. You can think of them, models for physical location inside the memory, okay? So these addresses become important, just like they are in maps. All right. Also, like maps, the memory that we use for computation is divided into different kinds of regions. One of the regions that we are going to specify is called stack memory. And the analogy is that it's a piece of the map, it's a piece of the geography that's maintained for you. You don't have to say, hey, it's not private property. You don't say, I want some of that and take care of it and maintain it. Somebody else takes care of it for you. So in the analogy, this might be like a school, right? Like we give our kids to the school, it does stuff, keeps them, does computation on them and sends them back to us. You guys are data at a school. Look, we're in a big stack. Ooh. Okay, so that's one piece of it. And the same thing is true in the machine. It is memory that is allocated and maintained for you in a very prescribed way. There's another region in memory that is much more free form called heap memory. I drew it larger because it is larger. You can kind of think of it as private property, except that you only ask for chunks of it of a particular size, and the system will give you that size. So you could say like, hey, I need a 4-bedroom house, and the real estate agent would go, okay, here you go. You wouldn't actually get to prescribe where that 4-bedroom house was, but you would at least get to say, I need one now, and I'll keep it for as long as I like, thank you very much. So we'll be talking about heap memory. There are other regions of memory that are important. There's a chunk where your code goes to be executed. So there's, this big piece of memory. It's not terribly big. There's this piece of memory that basically gives all the rules for how the rest of the memory should be manipulated. So ultimately, your for loops are represented somehow inside this piece of memory, okay, for everything that you run. And then finally, there's a special block of memory. And I can't yet come up with the analogy that fits with a map. I can't. Maybe there is one. But it's sort of the zero memory. You know what we call it in code? It's null, right? The zero memory spot. And the reason we even have it is because it gives us a nice mechanism for taking something whose value is garbage and initializing it to be something whose value is testable, is null. Okay, so that's kind of part of why it exists. All right, any question about all of this? I think you can tell that because I'm presenting it to you in such a high-leveled, allegorical way, I don't expect a lot of detailed, you don't have to repeat back. I'm not going to say, give an example of something from a map that you could use to represent a stack. I'm not going to do that. This is really just building your understanding and giving you a different model of thinking about memory if it helps. Okay, so let's make it more real. Let's make it more real. Okay, so we're going to start with stack memory. It's where the data associated with your program is stored. So, for example, you might say something like int x, like this. The system will see that and it will go, oh, yay, they need memory for x. And the system will go, I've got some. It's right here. Puts it in the sort of the next available spot, records the fact that your variable is named x, and specifies or keeps track of the fact that that x must be an integer. So after a simple declaration, you can imagine that x lives somewhere in stack memory like this. Okay? Any question about it? It's all right? Nothing surprising there. And moreover, if you say something like x equal 5, then, someplace in memory, some representation of the value of 5 is put here. Maybe it's notches on a stick. I don't know. Oh. All right, some representation of 5 is stored in memory. All right, so this doesn't only work for integers. It also works for any primitive type and any user-defined type. So I can declare sphere y, and the system goes, oh, yay, they need me again. I'm going to just go ahead and kind of on top of where I put X, I'm going to put, I don't know, let's see, maybe that's reasonable. I don't know. Depends what else is going on. Sphere Y, and the type is sphere, and the value is determined by the constructor, whatever constructors you have set up. Okay? And the size, the amount of memory that it needs, completely known. Okay? I kind of have it. Yeah, the amount of memory that it needs is known by the system. It's like it looks, says, okay, how big is a sphere? I'm going to make sure that I can allocate that much memory. Okay, and then we can do whatever functionality is allowed for a sphere. But I don't know about you, but this is all kind of boring, right? Like, I don't think I want to know the details of this part. But guess what? Things get more interesting very quickly. There's an entirely new data type, you might not have seen it before at all, whose declaration looks like this. So it looks somewhat familiar, and it's reasonable to guess that somewhere in memory, determined by the system, a variable is set up whose name is P, whose type is one of those things, which we interpret to mean the memory address of an integer. Oh. Okay, or shorthand, we say an integer pointer. And the reason for that is actually the goal of the next slide. We want to figure out some mechanism for making the value inside of P X's memory address. That is, we want to have X be an integer whose value is 5, P be some kind of pointer to X. That is some way of referring to X. The address, so P's value is the address of X. And the whole question is, how do we make that happen? What does this thing look like? What does this box look like? Any questions so far? This is intended to be pretty rudimentary. Good? Okay. So how do we assign to P? So we have this thing, we're calling it an integer pointer. Its value is supposed to be the memory address of an integer. We've got one, X. Okay, we've got one. So the question is, how do we assign to it? Here's an idea. You like it? So if this were not such a, if this were maybe a friendlier language, right? If it weren't such a, I don't know, if it were a more helpful language, perhaps the system would go, oh, you gave me, I wanted an integer pointer, you gave me an integer, I'll just read off X's memory address. But it doesn't do that. Instead, it says, whoa, the left hand is a pointer. The right hand is an integer. Broken. So type checking across that assignment statement is robust here. Okay, you're going to get a compiler error. It's going to go integer, pointer, no way. Okay, any question about that? So you can't do that. That's not how it's done. Nope. So here's another idea. Maybe you just say, okay, I'm just going to guess where X is, and I'm going to put a 20 here. So explicit reference to a memory address. All kinds of problems with this. We're not doing this either. All kinds of problems with it. Number one, we don't even necessarily know how memory addresses are represented. In this class, we don't know. It's not, 1452 West Green Street, We don't have control over it. It's the machine that determines what those addresses look like, and we don't have control over it, so we're not going to pretend to know. The other thing is that we don't know what addresses are attached to anything meaningful. We would have to ask the thing ahead of time, ask X, hey X, where are you located? And X would have to provide that information in order to make that assignment, okay? Well, that actually gets pretty close to what we do. And the question is, how do we do it? We have this operator. It's an ampersand operator, but we refer to it as the address of operator. Ampersand. It modifies a variable name, and it returns the memory address of where that variable lives. So, ampersand X returns X's address. So now, there's kind of an obvious assignment we can make. P gets the address of X. Okay? Any question about that? And now it works fine. So now here, ampersand of X will return me a 20 or whatever, however that is represented. And now I can plunk it into P's value. Okay? Any question about it? Okay, so there's an inverse operator that's kind of, anytime you introduce an operator, it's kind of natural to introduce the inverse operator at the same time. So I'm going to go ahead and do that. The inverse operator basically says, what's the value of the target of the pointer? So, and this operator, it's an asterisk, is called the dereference operator. It gives you the value of a pointer's target. Let me show you a second how to read what we've got going here. So here's another mechanism for kind of drawing a picture of what's going on in memory. This line right here says, make me an integer X. I'm going to pretend that we were smart enough to put a 5 in it, okay, just like the example shows. I mean, you could have X equal 5 here, okay? And now I declare another pointer, P, or another variable, P. It's a pointer type. I happen to draw that with that little dot right there to indicate the value that I'm going to put there is going to be a little arrow pointing to somewhere. And then if I execute this line of code, it simply means that P points to X. Okay, any question about that? That guy back there is yawning. And I don't blame him a bit. And now he's blushing. Oh, no, I'm not. He's still yawning. All right. All right. And the reason for that, the reason I don't blame him a bit, is it doesn't feel very interesting, right? Why do we care about P's memory address when if we want to mess with X, X's memory address via P, if we want to mess with X, we can just mess with X. But the deal is that these pointers have greater utility to us than just grabbing the memory address of something else that's already on the stack, okay? All right, any questions about anything you see here? All right, so let's look into that a little bit more deeply. Here we have stack memory, and here we have that ginormous chunk of other memory that we're going to refer to as the heap. Now, stack memory, as I said before, is something that you just have to ask for a variable. The system decides where to put it, and moreover, when you're done with that variable, the system cleans it up for you. Heap memory, on the other hand, you explicitly ask the system for a chunk of memory, and when you're done with it, it's your responsibility to put it away or finish it up. Okay, so let me show you how to get access to heap memory. So here's how it's done. So now I have this pointer P set up on the stack like this. There's no reason I switched those, just for convenience. It has no value. But to give it a value, to give P a value, I'm going to call a function called new, specifying a type int, and the system will go, oh, you want something from the heap. Okay, I'll go, how much do you need? Okay, I'll go find you a chunk of that size, and you can have it for as long as you want. Okay, so somehow, somewhere, the system goes out and it finds a chunk of memory, and it returns the address of that chunk of memory, and the assignment statement right there puts that memory into P's value. Okay, yeah? Yes, it's exactly the same as malloc in C. Okay, this is what malloc does, except you don't have to specify a size here. The system says you're always going to want the size, so I'll do the right thing. Okay, any questions about that? All right, so that means now that we've got this new chunk of memory, and we'll talk more about what it means that that you are responsible for putting it away yourself, for saying that you're done with it yourself, a little bit later on. But there was one more thing I wanted to do. Oh, I wanted to point out that this pointer mechanism is the only way that you can get access to this heap memory. And in fact, that's one of the primary purposes for these pointers in this class, is we're going to use them to kind of pass around handles to this memory. Now, the way to think about this heap memory is a place to put things that you want to have hang around. So for example, if we were programming a game, a chess game, okay, you and me, we're going to program a chess game, and you're one player and I'm the other player, we want to have, in a sense, a shared board, right? So this would be a mechanism, not the only mechanism, but a mechanism for us to specify memory that is used for the chessboard, and all we have to do to pass around access to it is to keep track of pointers or keep track of where it lives in memory. And we'll see more examples of that going forward. Okay, I have a question for you since we're not quite done. I'm gonna mix it up here a little bit. So I'm going to put Q somewhere. Q. It's also an integer pointer. When I do this, what happens? When I do that, what happens? Yeah? Right. Q points to the same place as P points to. That is, its target is the same. That means this value is the same as P's value, which means they both refer to this. Okay? Now remember, I said that I can access the target of a pointer using this dereference operator. So I can say the value of P gets 4. Where does that 4 go? The value of P, I follow this pointer right here, right? The value of P is 4. And now what happens if I do this? All of you say it. It prints out. Right, that's right. It follows Q. So now look at this. I have two different variables sharing or referring to the same chunk of memory. All right, any question about all of that? Yeah, Mark? Hold on just a second, guys. I need to hear him. Yeah?
Okay, so can you store a pointer inside the Q?
Sure. Yep, so the question was, could this thing that's now an integer, could it be yet another pointer? And the answer is, oh, sure, that's all of MP2, let me tell you. Any other questions? Yeah? Yes. Yep. We'll talk about that next time too. Okay. Bye, everybody. Hey.
So the no memory states